Hello, and welcome to the first video in section 13.1. In this one, I'm providing an introduction to vectors in the plane. So what does this mean? Well, in this video, we'll talk exactly about vectors in the plane. I'm going to define what these are. So I'll define these, define what a vector is, talk about what it represents. I'm going to motivate vectors a little bit, give you an idea of why we should be talking about vectors. I'll also we'll look at some terms and notation along with vectors, as well as some other things about vectors, some special properties, some special vectors, things like this. So let's get started. So first off, what is a vector? Well, a vector is a quantity that has both direction and magnitude. That is likely something you may have heard before in, say, a physics class or another calculus class. That's sort of the big thing, is that it has direction. Vectors have direction, two things, direction and magnitude. And that's it. Just those two things. So what's going to be really helpful for us is to introduce a model of vectors, which is arrows. So if I draw an arrow like this, so this dot and this dot, this arrow has a head and a tail. So we call this part the tail, where it emanates from. And here, this is the head, where it terminates. So these arrows, any arrow that I could draw on the plane, let me maybe draw a couple more examples, a few other arrows, so maybe something like this. Maybe, how about something like that guy? Yeah, it's also an arrow. Maybe one going up like this. Here's some examples of arrows. Maybe I'll need another one. Each one of these has a tail and a head. And the great thing about these arrows and why they serve as a model for vectors is because each arrow I can think of as just expressing two quantities, right? Each of these has a direction, a way that it is pointing, and a magnitude being the length of the vector. So in this case, this would be the distance between the tail and the head. So this would be our magnitude, is just that real number that represents how long the arrow is. That's magnitude. And then direction is, we'll talk more about direction later, how exactly we quantify direction, things like this. So each of these represents a vector. As you can see, for instance, take these two vectors. They seem to be pointing in the same direction. So these two vectors have the same direction, but different magnitudes. Now you might say, oh, I don't know if that's quite the same direction. That's sort of the problem with modeling these abstract vectors, these abstract things, is that you have to be very precise when you draw them. I didn't draw it super precise here, but we're going to say those two things have about the same direction. But they do have different magnitudes. They have different lengths. Notice these guys, these have, it appears to be opposite directions. But perhaps, let's see if I kind of make this, I tried to make these have same magnitude, but let's just say these have the same magnitude. Maybe I didn't draw it super precisely, but we'll say those have the same. So you can have all sorts of different combinations to look at any two vectors. If I take this vector and this vector, these have different directions and perhaps different magnitudes. Certainly this one and say this one have different magnitudes and different directions. All these different possibilities are there. And these are just vectors in the plane. So why study vectors? So why vectors? So let's say I want to keep track of, let me draw a little, I don't know, river here. How about? So these are the banks of the river, and let's say I want to, or maybe I'll do some blue in here. if you're colorblind, I apologize. This is blue to represent the water. So maybe this is a river, and maybe we want to keep track of, oh, I don't know, a leaf that's on the surface of the river, or maybe a boat that's going down the river, and let's say we're looking at it from above. So maybe I have, I'm going to go with a leaf. Let's say there's a leaf floating in the river. Now there's lots of different quantities, lots of different ways I can describe that leaf and how that leaf is going to change over time. And if I want to keep track of it, if I want to track this thing, I'm going to need to know certain information about it. So one thing I might know, so maybe if I pick, let's say maybe I'm standing right here, maybe I'm on maybe this is my origin. And so, origin, sorry. So let's say this is my origin. And I can measure where this leaf is relative to me at the origin. I can do this by drawing an arrow. I can say, I'm here, the leaf is right there. That's one way I can keep track of the position of this leaf. Let me label this with leaf. Let's say position. So I can tell you the position relative to another object, in particular where I'm standing right now, by drawing an arrow. That is, a vector describes its position. It is this far away from me in this direction. Now there's other quantities, right? If I just keep track of position, then I am tracking it, but how is this position going to change? We know position depends on velocity, acceleration, other higher order derivatives, things like this. And so another thing that I can do here is I can take this leaf and I can record what its velocity is. So let's say maybe the river's traveling east. Let's say this is northeast, southwest. Let's say it's traveling east, and so maybe there's another vector here that's describing the velocity. So this would be a velocity vector. Maybe there is also an acceleration vector. Maybe it's accelerating that way. Right, so again, all of these quantities, position, velocity, acceleration, they're not just a magnitude, but rather a position or a magnitude and a direction. I need to tell you how much it's accelerating as well as in what direction it's accelerating. Same with velocity. How fast is it going? That's the magnitude, as well as the direction. In what direction is it traveling at that time? And so an object moving in the plane, or as we'll see, we'll extend it to 3 dimensions. So let me just right here, we're going to extend to space, or that's 3 dimensions. We'll work on doing that. But the idea is, any object in the physical universe, there are all these different vectors that describe that object, what it's doing, how it's changing, things like this. They're all vectors. And so this is really nice. If we use we use vectors, if we study vectors, we will be able to better understand how things change. Now, this is not the only sort of example. For instance, so this is maybe more physicsy. Another physics example, maybe not velocity, acceleration, another vector that we'll see in physics. So let's say I have just a hanging weight, something like that. So maybe this is my weight. And I'm just going to draw it in the plane for now, but again, we're going to extend this to 3 dimensions. So let's say this is a ceiling, and let's say this weight is attached to a couple strings hanging from the ceiling, something like this. There's a force diagram that I can draw here to better understand what are the forces acting on this weight. So one, I know that gravity is acting on it. Again, gravity, that's a force. Forces also have direction and magnitude. Gravity is pulling it down. Its strength is equal to the weight of the block. And the direction is straight down towards the center of the Earth. And so that's a force. So I'll call this one G. Sorry, give me 1 second. I need to smaller. So I'm going to call this one G. And to indicate that this is a vector, I'm going to draw a little arrow over it like this. G vector. So it's telling this variable, or rather constant G, has a direction and a magnitude. But there's a couple other forces acting on this, namely the strings that are holding this thing up. So this would be the tension in the strings. I'm going to call this T1, put a little arrow over it, and T2, put a little, oops, not T squared, can't really square a vector. T2, put a little arrow over it. So I have these three forces acting on this block, and if I understand these vectors that are describing these forces, then I can better understand the properties of this system of this block being held up by two strings. Of course, both of these are very baby examples. We're going to do much more advanced things than this as we go through the course, but here are at least two examples from physics. Now, I'm just going to start with these physics examples. I know not everyone is a huge fan of physics. We are going to see a lot of physics examples, but I promise you we're going to bring in other examples. So, for example, we'll do some economics type things where things will be a little bit more abstract, which is why I'm not quite mentioning them yet. But just think we have, let's say, a price of some instrument, some product, something like that, that depends on two other things. So maybe some other variable x and some other variable y. And I'd like to know how that price is changing. And so what I can use in this situation, if I have price depending on two other things, I can use vectors to model this as well. And we can talk about direction and magnitude, even if we're not exactly in space, in the real world. We're speaking more abstractly. At any rate, there's lots of quantities and lots of different fields that are described by vectors, and so that's sort of the point. These arrows are our guide. So we're starting in 2 dimensions. We're going to understand the geometry of these things. We're going to extend this to 3 dimensions, understand the geometry there. And as we move through the course, we're actually going to extend past 3 dimensions to places that we really can't visualize anymore. But we're going to carry our intuition that we develop in 2 dimensions and in 3 dimensions up to higher dimensions. All right. So let me stop rambling about that. Let me just cover a few other things here. So some important pieces of information for vectors. As I mentioned, they have both length and direction. We'll talk a little bit more about how we quantify these things, how to quantify. So right now I'm sort of just thinking of vectors geometrically. We're going to put these things in the Cartesian plane and later in space, and we'll be able to define exactly what their length and direction are. So that's sort of one burning question right now. How exactly do we quantify direction? Magnitude, I mean, is length, but how do we quantify direction? We're going to get to that later. 2 vectors are equal if they have the same magnitude and direction. So this is an important one because it doesn't matter where I draw these vectors. So for instance, if I draw, let's say, this vector, and then let's say I just pick this vector up and plop it over here. Maybe I move it over here. These are the same vector. So here, if I call this vector, let's call this u that I've defined here, and I call this vector v. They may be in different places in the plane. It doesn't matter. These 2 vectors are the same. They have the same direction and they have the same magnitude. These 2 vectors are exactly the same. This is what I mean when I say a vector has direction and magnitude, but that is all it has. Those are the only 2 things that are kept track by these arrows. I don't care about where they are in the plane, just what their direction and magnitude are. These 2 things are the same. So scalars, let me actually jump up to this slide again. Scalars are used to grow or shrink a vector keeping the same direction. So for example, these 2 arrows here that I've drawn, these 2 vectors, they have the same direction but different magnitudes. What that means is that this, let's say this little vector is a scaled version of this bigger vector. I've multiplied it by a real number less than 1, and that has made it the magnitude smaller. So these are what scalars do. We'll talk more about how these interact with vectors in I think the next video. But in this case, scalars are real numbers. So these are used to either grow or shrink without changing the, well, I shouldn't say without changing the direction. So let me jump back up here again. This vector going down like this vector going up. They have opposite directions but the same magnitude. What this actually means is if, let's call this vector Oh, let's call this vector u. Again, I like using u and v. And let's call this vector v. If they have the same magnitude and exactly the opposite directions, this is also the result of a scaling. Excuse me. This is also the result of a scaling. In particular, they are negatives of each other. So this is what the negative of a vector is. It just flips the direction. So what we say is any two vectors that either have the same direction or opposite direction, these are scalar multiples of each other, and we call these parallel because, well, they look parallel. They're going in the same direction or perhaps the opposite direction. So that's, yeah, a little bit about scalars. Again, we're going to get more into scalars later. One thing I want to bring up here is the zero vector. So as we'll see, we're gonna have a bunch of operations on vectors. We'll be able to add vectors together. In some sense, we'll be able to multiply vectors in a couple different ways, actually. We'll have scalars multiplying with these vectors and operating on these vectors. So what we're going to build up here is a whole algebra of vectors. They form what's called a vector space, which is a kind of algebra. And in this vector space, we're going to need a zero vector. So a vector that does not have, that has zero magnitude and has no direction. So this is sort of the exception to vectors having a magnitude and direction. The zero vector has no magnitude and no direction. So a little bit of a note on notation. When I'm drawing or writing, I will use the arrow because this is a boldface is harder to do. So this is the zero vector here. And this is just the real number 0. These are two different things. This is a vector representing that something that is typically described with a magnitude and direction at this instant or at this point has no direction and no magnitude. It is, if you're thinking of an object, it's not moving. Here, this is the scalar 0. So it's not telling me anything about direction. It's a different sort of object. It's a scalar. So yeah, notationally, I'll use arrows over the vectors. If I'm typing, and we'll see this in the book as well, boldface also is used to denote vectors. That's how I can get around these two symbols and make them distinct. So we use either boldface to indicate a vector, or again, if I'm drawing or writing, a little arrow above it. So something like this, U, that's a vector. If I am writing and I just say something like U, this would just be a quantity. Again, this would be a scalar. Typically, we won't use U for both vectors and scalars. I'm just trying to point out that if there is confusion, look for either an arrow or a boldface. If it's neither arrowed or boldface, then it must be a scalar. Typically, we'll use things like T. So maybe I'll change this to like a T. Something like T is a scalar. Right. So another thing here is when we start putting these things in the plane, and this is sort of our first hint on that, in the Cartesian plane, I know there are two, we can plot points in the plane, and then I can draw a vector from one to the other. So as I mentioned up here, this terminology of tail and head, well, if I'm in, let me draw a quick Cartesian plane here. So here's my x-axis. Y-axis, and maybe P is here, and maybe, I don't know, let's put Q down here. So if I just plot 2 points, well, I can draw a vector with tail at P and head at Q. Sorry, that's the tail. And that's a well-defined vector. So given 2 points in the plane, I can draw a vector between them. All right, so that's about all I want to talk about in this video. We've learned a little bit of terminology. I've tried to motivate vectors a little bit and give you a sense of why we should study them. And we've talked of a few caveats of dealing with vectors, namely that now we have two sort of different kinds of objects. We have both vectors and we have scalars, and we're going to get into how scalars can interact with vectors and how vectors can interact with each other. We'll get into that in the next couple videos. See you there.